Hello students! In our previous video, we learned about the electric motor and its uses in various electrical appliances like fans, pumps, etc. As we know, electrical motor works on the principle of conversion of electrical energy to mechanical energy. But students, can you think of reverse? Can we convert mechanical energy into electrical energy? Yes, we can. One such phenomena in physics allows us to do this. It is called as electromagnetic induction or EMI. So in our today's video, let us learn about this phenomena involving electricity and magnetism called EMI. Students, we can hardly imagine a present-day life without electricity. But do you know how electricity is generated? Yes, you are right. Electricity is generated in hydroelectric power stations using this phenomena of EMI, that is electromagnetic induction. So to understand this phenomena, first we'll have to recall Ørsted's experiment and also look at Faraday's experiment. Recall students, we learned that during his experiment, Ørsted found that current carrying wire behaves as a magnet. That is, magnetic field can be produced by passing electric current through a conducting wire. So from his experiment, we know that electricity produces magnetic field. But can magnetic field produce electricity? Let's see. For that, take a bar magnet and a copper coil with several turns. Yes students, copper coil with several turns is nothing but solenoid. So students, you know that bar magnet has its own magnetic field. So what will happen when this bar magnet is moved in and out of a copper coil with several turns, that is solenoid? As observed, it results in the generation of electric current in the solenoid. This was observed first in 1831 by Faraday. Faraday, through his experiment, found that a moving magnet with a magnetic field inside a coil can generate an electric current. At that time, he called this phenomena as electromagnetic induction, which allowed him to convert mechanical energy into electrical energy. Yes students, so now you know that it is possible to convert mechanical energy into electrical energy. Now during his experiment, as you know, Faraday made a solenoid of large number of turns of a copper wire and connected its ends to a galvanometer to detect the presence of current in the circuit. Students, when there is no current flowing in the circuit, the pointer of galvanometer remains at 0. And when there is a current flowing in the circuit, the needle of galvanometer deflects, which shows the presence of current. Remember students, a galvanometer does not measure the amount of current. Instead, it only indicates whether the current is present or not in a circuit. Now students, Faraday moved a bar magnet which he took in and out of the core of the solenoid. And he observed a deflection in a galvanometer when the bar magnet was inserted into the coil. He also observed the deflection in galvanometer when bar magnet was taken out of the coil. But he also noted an interesting fact that at both the times the deflection of the needle was in the opposite direction. Say if there was a deflection to the right when bar magnet was inserted in the coil, then the deflection was to the left when magnet was taken out of the coil. This change in direction of deflection indicates the change in direction of the induced current. So from this, he concluded that when a bar magnet was moved in and out of the coil, there was current generated inside the coil. The direction of the current generated depends on the direction of the magnetic field. This current so generated in a coil is called as induced current. Students, he also observed that no current was induced when the magnet is kept steady near the coil. So one important conclusion was an electric potential difference is induced in the coil only when there is a relative movement between the magnet and the conductor. In other words, we can say that if magnetic field is constantly changed, only then the current is induced inside the conductor. This phenomena is called as electromagnetic induction, as we are using change in magnetic field to induce electric current. Now students, if we insert the north pole of a magnet inside the coil, the galvanometer shows a deflection in one direction. What will happen if we insert south pole of the magnet inside the coil? Yes, the deflection is in the opposite direction, indicating the change in direction of the induced current. But students, have you ever thought what will happen if magnet is kept stationary and coil is moved near a bar magnet?
Well, you think about this and we will see you in the next video.